Okay, good afternoon. Welcome to the last session of Compounds Wednesday in the semester. I almost had forgotten that Lisa still needs to give a 45-minute seminar in AMP before she can defend her PhD, so that's happening this afternoon. So Lisa has been here for almost 5 years now. She started in 2014 to work with me and Hans Graeber on these things that she will present today, and she is now planning to defend her PhD in early July. Before coming here, she was at Palm Beach Atlantic University and got a bachelor's degree in mathematics with a minor in oceanography. And then other items here in the list are that she got the Palm Beach County's Women of Distinction Scholarship in 2014, and she was a recipient of the Outstanding Graduate for Mathematics Award at Palm Beach Atlantic University. She has attended 4 international conferences and 3 project meetings. She has published 3 conference papers and 3, and there are 2 more.
Two first authors.
No. They are all conference papers. 3 conference papers. So 2 as first author, indeed. I didn't want to mention that. And 2 longer manuscripts for full peer-reviewed articles are in preparation. She has participated in 3 cruises while she was here, spending 47 days at sea. In addition to that, she already spent 15 more days at sea on 2. I think one of those other cruises was on the Walton Smith already, but that was not related to your project. So there are even a few more days at sea, but 3 cruises for this project, and she will probably talk about those experiments. And the only additional noteworthy item I found here in the CV that I found a little funny, under skills, she emphasizes here exceptional instinct for software design. So that's quite good, I think. 45 minutes. Should I read the title? No, it's too long. You can say what the title is.
Yeah. Thank you, Roland. Okay, hello everybody. My presentation will be about using advanced Doppler Marine Radar techniques to measure surface currents and to study internal waves. And typically the 45-minute Compass seminar would be a kind of a dry run for the dissertation or for the defense. And this is a dry run for 2/3 of the defense. I still have one part that needs a lot more work, but I'll be discussing 2 of my chapters in the seminar. Just an overview of what I'll be talking about. The first part is about Doppler-derived currents, and I discuss why we need Doppler-derived currents, how do we get Doppler velocities, what's the relationship between the Doppler velocity and how we get the surface current out of that. And then I will explain my algorithm, which is called the Doppler Velocity Synthesis algorithm, which gets a 2D vector field around the ship of surface currents. And then the second part of this is about internal waves. And first I just give a little introduction on internal waves, and then I talk about how Doppler velocities can help us to understand internal waves and what other internal wave parameters we can determine with our radar. So I have been on 3 research cruises in the Pacific. The first 2 were in the Western Pacific. Both of the first 2 were on the Roger Revelle, which is a research vessel owned by Scripps Institute of Oceanography. And the first cruise was in May of 2016 off the northern islands of Pullout. The second cruise was in March of 2017, left out of Taiwan and went through the Luzon Straits. The third cruise was off the coast of Point South, California, which was, and it was looking at the inner shelf dynamics. And that was on the RV Oceanus, which is a much smaller ship, and that was mostly looking at internal waves and such, so that's where a lot of the internal wave stuff comes from. On all three of these cruises, we installed a Doppler Marine Radar, which is a coherent X-band VV polarized radar that gives completes one rotation every 2 seconds with 4,000 pulses per rotation. It can see data in a 3.2 kilometer radius around the ship, and you can see in this, you can see that we put it on this corner of the Roger Revelle, and it's not the tallest thing on the ship. There are other things that are taller than it. So you'll see in all of my radar images, there's little slices taken out from the shadowing from physical barriers. And in all of these cruises, we wanted to get surface currents. And usually when you want to measure surface currents with marine radar, you use the Dispersion Shell technique, which was originally developed by Young in 1985. It takes a 3D FFT of a radar image sequence, and it determines the velocity of the waves. And then it determines what their velocity should be without a current. And then the difference between the two is the current that the waves are riding upon. And that's how it determines the near surface current. And this has been around for a long time. It's accurate, it's well developed. In a recent study in 2018, the RMS was found to be only 4 centimeters per second in magnitude and 12 degrees in direction. And the downsides to the dispersion shell technique are that it needs waves. So we need wind speeds of about 3 meters per second or more in order to have waves that we can resolve. And it has a vector resolution of about 300 meters, which under normal circumstances would be under the pros column, but in certain situations we want to see what's happening in these small scale areas, such as the interface of a current front or an internal wave. So to fill this gap, we use the same coherent marine radar data in a different way. The radar does not need to be coherent to do the dispersion shell technique, but because we have a coherent radar, we get both intensity information and phase information. And here's an example of a single rotation for intensity and phase. And the intensity images is what people are used to looking at when they look at radar images. You have wave patterns in here. And the phase image in and of itself doesn't help you that much. It looks like a bunch of noise. However, if you take the phase difference between two areas that are looking at the same scatterers over a very short period of time, the phase difference is a very important measurement. So putting this into polar coordinates to kind of get a better feel for it, and zooming in on this corner right here, we take the phase difference between subsequent pulses. So we take this column minus this column, and then do that for every single column in the polar phase image, and we end up with a phase difference image. And you can see we have wave motions in here, so we must be doing something right.
How do you deal with wraparound?
I'm sorry?
Isn't there a wraparound problem? I mean, when you're taking phase differences, the phase is defined modulo 2 pi, right?
Mm-hmm.
So isn't there a wraparound?
There is, but usually these scatterers are not going fast enough to wrap around. There is a limit. It's about like 15-ish meters per second. And so if it's going further than that, or more than 15 meters per second, or less than negative 15 meters per second, then it would have wraparound, but the likelihood of that happening is pretty low because it's the sea surface, it's not going at 15 meters per second. And then, so putting it back into Cartesian, we have a phase difference image and a intensity image, which we can use to get Doppler velocities. So from the phase difference image, first thing we do is we eliminate the noise and we mask the physical barriers that I was talking about. We eliminate the noise by determining coherence for every pixel, and then having a coherence threshold and throwing out anything that's above that threshold. And then the next thing we do is a velocity calculation using this formula, which is based upon the radar geometry and some parameters of the radar itself. And then we have the Doppler velocity which is radial in each look. So in this area right here, it's going at negative 10 meters per second in look direction. So this is going this way, here's going this way. And then as we average the Doppler velocity, we get cleaner and cleaner data. So this is an 8-second average at 4 rotations. And then you can see in the intensity image, the wave patterns are kind of going away, they're averaging themselves out. And then the Doppler velocity is getting cleaner and we can see it at further range. And then here's a 30-second average. And so being that we have 1 rotation every 2 seconds for 38 days, we have a lot of data. So we needed to determine how to quantify it and be able to look at it, because it's not humanly possible to look through every single rotation. So what we did was we took the range at 135 meters, which I'll explain later why we did that, and you plot it with respect to the angle from north, and you can see that it has this sinusoidal shape. So we fit a sinusoid to this, and we end up with the parameters of the sinusoid, which is magnitude, direction, and offset. And then you can convert that to meridional, zonal, and offset. And those 3 things get stored in the computer, and then we move on to the next image. And we do this every 256 meg, so that's approximately every minute and 15 seconds, or 37 rotations. And the first time we did this, we did not correct for ship motion, just to make sure we're doing it right. So then we plotted it. This is the zonal and meridional components of the Doppler velocity compared to the zonal and meridional components of the negative ship motion. And it lines up fairly well, so we said, okay, great, we're doing it right. Now let's do this again, but with ship motion correction. So we did this, and this is for pullout, and we have these time series of zonal Doppler velocity, meridional Doppler velocity, and sinusoidal offset. And we also have a ship track that is paired with this data, so this is also geospatial data as well. Now, according to Carrasco 2017, the Doppler velocity is made up of these contributions. So it's the speed of the Bragg waves, the wind drift, the surface current, the orbital motions, wave breaking, and wave shadowing. And so trying to empirically come up with a function that includes a lot of these, we assumed that the Doppler velocity is a function of wind magnitude and direction, perpendicular wind magnitude and direction, which is from a ship-mounted anemometer, the surface current, which is either from the Dispersion Shell currents or from an ADCP, the signal-to-noise ratio, the Bragg phase velocity, the difference between the Doppler velocity direction and the wind, which is important in wave shadowing, and the incidence angle. And we want to solve for surface current. So we put all of this into one big regression and tried to figure out what it spit out. So here are some of our results. This is for pullout. You can see that it lines up, visually it lines up fairly well. The blue is the ADCP currents at 13 meters. That's the uppermost bin that we have that's useful from the ADCP. And the red is the Doppler function. And the scatter plot on the left is color-coded with respect to cosine fit mean absolute error, which is basically data quality. So really noisy data is red, and really clean data is blue. So it's great because our really clean data is close to the y=x line, and our really noisy data is not. So this is what we would expect. This is for the inner shelf cruise. Again, we have a mean absolute error of only 7 centimeters per second, and visually it lines up really well with the ADCP, and this is ADCP at 3 meters, which is our uppermost bin. And the only time we have some problems is around your day 253. There's something crazy happening, but for the most part, it lines up fairly well. And Taiwan, we have excellent, excellent results. Visually, it just looks great. Sometimes in some areas, you can't even see the difference between the red line and the blue line. And we have a correlation of 0.97 with a mean absolute error of 8 centimeters per second. And this is all 3 cruises plotted in the same way. So this is also color-coded by data quality. So the black and the purple is the best data, and then the red is the worst. So the best data does follow the line pretty well. And the reason that Taiwan was so good is because the Taiwan sea state was much higher than in Palau or in the Intershelf cruise. We have some really, really big waves breaking over the bow, and because of that, we have really good signal-to-noise ratio, and you can see further out, and you have less noise in your Doppler data. So I think that's why the Taiwan data is so good. And this is for 47,000 images.
Excuse me, Lisa, the ship motion or the high seas is good in terms of signal to noise, but doesn't the ship motion create all sorts of processing problems for you?
So being that this is an average of about 1 minute and 15 seconds, I assume that roll and pitch kind of cancel out a bit. I do correct for ship movement, but not for roll and pitch.
Okay.
So in order to get a vector field for this, I developed the DOVES algorithm, which is the Doppler Velocity Synthesis algorithm. And instead of fitting an entire sinusoid to the whole image, it fits pieces of sinusoids to pieces of the image to get a vector field. And there's 2 modes. There's stationary for a non-moving ship or land-mounted platform, or a non-stationary for moving vessels. Here's an example of how stationary works. So we break the image up into 24 pieces. Each of them are 760 meters long in range and 45 degrees in azimuth. And in each of these little boxes, we have, I believe it's a 10-minute average of the radial Doppler information. And we can fit a sinusoid to this little piece, and then the same thing in another part. And then we end up with this, it's a vector field, but it's not a uniform vector field, because as you get further and further away from the radar, 45 degrees takes up more and more space. And DOVES non-stationary is using a moving ship to our advantage. So say we wanted to determine the Doppler velocity in this little square. As the ship goes by, it looks at that little area from different look directions, and from that you can determine, you can fit a sinusoid to that data. Usually it's not a full sinusoid. Usually it's half or 3/4 or something like that, depending on how the ship is moving. And once we started to make some DOV products, we realized very quickly that there is a range dependence. So you can see in this one that closer to the ship, this black line here is the ship track. Closer to the ship, the vectors are smaller than further away from the ship, and this should be a uniform field. So this is plotting the range dependence. So on the y-axis we have the magnitude ratio, so it's the magnitude at that range bin divided by the magnitude at 135 meters. And remember, forever ago, I talked about that I held the range at 135 meters. Well, this is the reason why, so we can normalize it with the 135. And so it has this square rootish kind of shape, and then once you determine the shape of the range dependence, then you can divide out by it and you have a uniform vector field. And so as I was doing this, I said, oh yeah, easy peasy, you just divide it out, no big deal. And then so in this case, it's arching up in the one that I just gave. Sometimes it arches down, and sometimes it does nothing at all. So it took me a long time of pretty much 2 months of doing exclusively this and just staring at scatter plots until I tried to figure out what the range dependence actually depends on. So I plotted the range dependence. This is for 11,000 images. I plotted the range dependence along with the range here, and then I quantified it by calling it this variable q times the square root of the distance, since most of them follow this kind of square root-ish shape. And then I can set the magnitude ratio at 135 equals 1, because of course the ratio between 135 and 135 has to be 1. And so again, after staring at scatter plots for 2 months straight, I discovered that it depends on the wind direction, the Doppler magnitude, and the Doppler direction. And this is a prediction of Q with the empirical function that I determined for Q. And here is the predicted data based upon that Q function for this plot right here. So great, now we have the range dependence done. Now we can actually have some Doves products. So here's an example of what one looks like. Here is the original Doppler velocity. We apply the Doves function, and then we end up with this cool-looking wind-driven eddy. This is an example of Doves compared to the dispersion shell. So on the left in the yellow is dispersion shell currents, and then on the right is the Doppler-derived currents. And you can see that, so right here is a front coming through. It's difficult to see from this angle, but there is a front coming through, and it's less the front coming through and more just the ship going through the front, but you get the picture. And the current is overall northwest before the front goes through, and then northeast after the front, and both of these portray the same. There is some discrepancies, especially right by the front, that Doves does not handle all that great. And also right near the ship track, sometimes we get weird vectors, because if the ship is looking at something straight ahead and then again it's looking at it straight back, it doesn't have a range of look directions to synthesize, so it picks something weird because it doesn't know what it's looking at. Now for something completely different, I wanted to talk about internal waves. So the whole point of this project was to get to this small scale region, and we wanted to look at internal waves because we had a ton of them during the inner shelf cruise, and we thought that would be really interesting to see what it looks like in the Doppler information. And so we have, what's cool about the inner shelf project is we have these echo sounder images that show the shape of the internal wave underneath the ship, and we have the radar data which shows the spatial distribution of the internal waves. So very quickly, internal waves, especially the ones on the shelf, come from tides. So during ebb tide, there is a perturbation of this kind of upper top water as it goes off the continental shelf. And then during slack tide, this relaxes. And then during flood tide, this gets propagated back towards shore, often in a little train of a few of them. And then that's where the internal tides come from that we're seeing in these radar images. And on the surface, they appear as these linear slits. So this is this is just a picture I took with my iPhone at the same time that this radar image was taken. And these black streaks in the radar image are these kind of smooth areas on the sea surface. So you can see them with the naked eye. And so we know that internal waves have intensity signatures, but we wanted to see if they have Doppler signatures as well. So we have, and the answer is yes, they do have Doppler signatures as well. You can see these stripy patterns coming from the internal wave. And the reason for this is because of the convergence and divergence that the internal wave causes on the sea surface. And so, I know this is a complicated figure, but just bear with me here. So on the leading edge of the internal wave, there is a convergent zone, which leads to rough water and a bright radar return. And then on the trailing edge of the internal wave, there is a divergent zone, which leads to smooth water and a dark radar return. And then, according to these current variations, the Doppler variations should vary in this way, but completely out of phase with the internal wave itself.
Excuse me, Lisa, is there sort of a chemical difference associated with surfactants, associated with the difference between the regions where there's divergence and convergence?
So the surfactants do often collect in the convergent. Hold on, let me think of this. Surfactants do collect in the convergent regions, but the radar imaging itself is just purely based on the radar imaging theory. We're just talking about the roughness of the water, but there you do see surfactants definitely, especially in lower wind conditions when maybe you don't have as good SNR, and then you see like kind of these dark slicks of surfactants that are stuck in the convergent zones. But for this analysis, I'm talking mostly just about the surface roughness theory. So what we do is we find an internal wave, and as the ship goes by, we have the echo sounder image underneath the ship, which is the shape of the internal wave. And then in little rectangular boxes that are aligned with internal wave orientation, we do the Dove's algorithm in each of these little rectangles. And from there, we can fit a sinusoid to each of these regions and then determine their component in internal wave propagation direction. And this is a moving search window because the internal wave is moving over the course of our synthesis time. So we do that fairly simply, even though it's a complicated geometry problem, but the explanation is pretty simple. We take the leading front, we take the leading internal wave of an image, say, in the beginning of our synthesis, and then we take the location of the leading internal wave in the image at the end of our synthesis. And then we determine the time difference between the two images and the difference between that it's traveled and then the velocity. So it's a moving search window as the internal wave moves. And so here is one of our results. So this is our transect right here along these internal waves. And the pink plot over here, the black, so each dot represents one of those rectangles that was synthesized, and I colored it black. So I have a threshold for bright and dark pixels, so I colored it black if I'm considering it a dark pixel, and coloring it white if I'm considering it a bright pixel. And on the y-axis here is the Doppler velocity anomaly, and then here's the meters long transect from left to right. So zooming in on this figure, the peaks in the Doppler velocity anomaly correspond to an eastward flow or an eastward anomaly, and the dips in the Doppler velocity anomaly will correspond to a westward flow. So that would mean that the convergent zones are in between the eastward and the westwards, and the divergent zone are between the westward and the eastward. So in a perfect world, all of these regions would be black and all of these regions would be white. However, it's a little bit shifted. So we wanted to do this on a couple more internal waves and determine, is this a pattern? Does this always happen? When does it happen? So here is another transect that we did. Here is the internal wave under the ship, and here's our transect. And here is another type of plot of the same kind of data. So the blue here is the pictocline depth, which is determined from the echo sounder. The red is the Doppler velocity, and the black is the intensity. So you can see that these are all kind of varying at the same frequency, but not all at the same phase. So we set up a sliding maximum cross correlation to determine where the peak phase shift that these all line up in. And so after doing this, we determined that the Doppler variations are phase shifted 35% of the internal wavelength, and the intensity variations are phase shifted 17% of the internal wavelength. And don't worry, I'll explain that in a minute. I know that's a lot of words. and we did one bore just for fun to kind of see what it looks like. So the pictocline depth, you can see that it just drops off real fast, and the Doppler velocity also has this drop, but the intensity has this spike. So it will end up this is what it looks like in the radar image. You have this big bright spike where the bore drop is, which is really interesting. This is the theory of what Doppler variations should look like with respect to the internal wave. Here's what we're actually seeing. So it's a little bit off, but fairly close. But it's kind of neat because, to my knowledge, no one's done this before, and it's just a really cool analysis. But it doesn't necessarily line up perfectly with the theory. Now, also, I want to talk about the intensity data. So we have internal wave images over all of the over the whole coast, and I painstakingly went through all 15,000 of them, and I categorized them into different categories. And so the three categories are rough linear features, which are those spikes that I was talking about. It's just a bright line. There is a dark internal wave, which is a dark linear features over a gray background, and then there are what I'm considering to be regular internal waves because it's bright and dark alternating streaks on a gray background. And so we see the RLFs mostly in these shallow depths and lower wind speeds. We see internal waves at moderate depths and moderate wind speeds. And in general, we see these dark internal waves at deeper depths and higher wind speeds. And then every once in a while, there's an outlier. And so also what I did is I separated each of these into what they look like in the echo sounder images. So the echo sounder images are also broken up into three categories. So there's the bores, a depression wave, and a regular internal wave. And then so this is a bar plot saying how many RLFs are bores, which is blue, or how many are depression waves, which is red, and then how many are regular waves, which is yellow. And you can see in general, a lot of the bores, a lot of the RLFs are bores, a lot of the alternating black and white pattern ones are regular internal waves, and a lot of the dark internal waves are these depression waves. So, looking at the probabilities of this, a bright linear signature is likely to be a bore. A bore is also likely to be a bright linear signature. An alternating bright and dark signature is likely to be an internal wave packet. An internal wave packet is also likely to be a bright dark signature. A dark signature is most likely to be a depression wave packet. However, a depression wave packet is not significantly correlated with anything. So, although most of the dark internal waves are depression waves, not all depression waves have a dark signature. And usually the depression waves, so there's a 35% chance that a depression wave is a dark internal wave, or it has a dark signature, and then there is a 41% chance that it has an alternating bright and dark signature. And finally, just talking about some of my future work. For the Doppler currents, for the first section, I would like to retrain the regression and see if I get better results. For the internal waves, I want to compare the Dove currents above the internal wave to ADCP. We have this side-mounted ADCP that I have not had the full resolution access to up until very recently, so I want to compare the two. I want to also determine the shoaling speed of internal waves, since I have already a usable algorithm that determines internal wave velocity. I want to follow one as it gets closer and closer to the coast and see how it shoals and how it refracts. And then in some of the radar images, we find reflections of internal waves. So you see one coming into the coast, and then it hits the coast, and it kind of comes back and propagates in the other direction. And we want to see, does that always happen in certain conditions, or where, and why? And thank you. That's it. And if I could have a request, being that this is a dry run for the dissertation, for the defense, if there was anything that you felt like a complete deer in headlights in, please let me know so I can rework it for the defense.
The phase shifts that you pointed out were kind of interesting. Do you care to speculate on what the cause might be?
I don't know. It's probably a combination between kind of what you were saying, the surfactant theory, and the just the modulation of the current theory. There's some happy medium between the two of them, and that's what actually happens in real life. Also, every once in a while, that 35% and 17% doesn't always jive. Like, there's one internal wave we did that everything lines up perfectly, and we have no idea why. Like, it's just a weirdo in the data set. So it would be interesting to do more just to kind of figure out where that comes from, but right now, I don't know yet.
I have a couple questions, if that's okay. When you're doing your transects on the internal waves, and you showed like on one side with like a series of them, and then you averaged over them, you had like these
the boxes.
The boxes, yeah. Decide.
No, I go by. So each box is defined as how far. So being that my epicenter data is temporal data, and then the radar data is spatial data, I had to kind of have a mix of the two. So it's each width of each rectangle is defined as how far the ship has gone in 9 seconds from that pixel of the epicenter image.
But I mean, the angle of them is like
the angle is so I say, okay, here's like I pick a spot on the leading internal wave, and then I pick another spot, and then you can determine the angle between those two.
So it is kind of visual.
It's somewhat visual, yeah. I mean, it's like I zoom in really close and try to pick the best part, but it is somewhat visual. It's not automated.
Okay. And then I just missed it, but I didn't really understand what the 135 meter thing was.
So that's something I've actually been having a really hard time explaining. No, it's not your fault. It's it's something so the range dependence had to be normalized with something. There had to be a magnitude ratio in order to get the range dependence.
Yeah.
And so I chose the magnitude ratio to be normalized by 135 meters. And then I actually had to rerun the whole regression like in hindsight, because I didn't realize that the range dependent was going to be as important as I thought it was going to be. And then I think I originally ran it as just like an average of the whole image, but then I realized that once I needed to include the range dependence, I needed to normalize it with something. And I chose 135 because it's close enough to the radar that I have decent signal-to-noise ratio, but it's also far enough that it's not in like the shadow, like the wind shadow of the boat itself.
There's some decisions on it. It wasn't just like 135 meters. Like
there was a definite decision.
I just didn't understand what the significance of 135 meters away from the radar was.
I mean, it's arbitrary. It could have been 200.
Okay, but you had reasoning.
Yeah.
Okay, and then this is not so much a question, but just it's been a while since I've taken waves, so this might be really silly, but your last bit about what's a Bohr versus or what's like a linear feature versus what's an internal wave versus those things that look like internal waves but they're in the deep ocean. I just wondered, like, could you go back to that slide?
To like these or more to like
I think
the
there was
Bohr
one before where you kind of show all of
these?
Yeah. So you were saying like the last one, the deep water, deep ocean,
dark.
You called them dark internal waves. But in the end, it was that they might be they could be internal waves, or they're not necessarily those dark internal waves. They're not necessarily the depression waves.
Correct. Yes. I probably should edit my what's the name of a bunch of letters? Put it in an acronym. I should probably change my acronyms for these because it does get kind of confusing. But the DIW is for the signature, and these are the signatures, and these are the vertical profiles.
So is it safe to say that when you see that third one, what you call a dark internal wave, that you don't immediately know what that is?
Hold on. When you see a dark internal wave, it's probably a depression wave. But if you're just looking at the echo sounder, it's not necessarily going to have a dark signature.
Okay.
Sam?
So when you were determining what affected the range dependence, you said that it was wind direction, something else, but you didn't mention wind speed. Is there a reason why wind speed doesn't affect the wind?
I thought I had wind speed in there. It's been a while since I did the range dependence. Hold on, let me check.
I just didn't know if that had something to do with the shadow.
You're right. That was the one that. So I mean, I played with so many different variables, and then I actually stumbled upon the one that I had almost by accident, just by plotting things and different color codes and just literally staring at scatter plots until I found one. And then the thing that had the best correlation by far didn't include the wind magnitude.
Yeah, that's interesting. I wonder if it has something to do with the shadow of the boat. I don't know why that would be.
I don't think it's the shadow of the boat. I think the biggest thing is the wave shadowing is what's causing the range dependence. So if I was to model that physically rather than empirically, I would determine the height of the wave and then how much it was shadowed, because it's taking out that much each time. But being that I'm modeling it empirically, it's really just whatever works, and then this worked really, really, really well.
It's almost like a layover effect, right? Like, is that sort
I'm
of?
not sure what a layover effect is.
Like in SAR, when you have like a height on something, and then it can lay over the position of it, almost.
Less of that, more of like say you had a flashlight and you're looking at and I have a flashlight and I'm looking at this desk, then there's going to be like a teeny tiny shadow after that, and then so I'm going to see more of the microphone and then nothing of this table.
Mm-hmm.
So if the microphone's going a certain speed and the table's going a different speed, then I'm not going to see any of the table.
Then, yeah. Sorry. But then certain wind directions would have a wind speed dependence, right?
Certain wind.
So if you have a particular wind direction, then that wind speed dependence would matter. If you have it at, like, the shadow wouldn't be there, right? Or no,
it's more about waves than about wind. And I know the two are correlated, but
yeah.
say you just had like a gust of wind and it didn't have time to make the waves yet, then that it wouldn't be fully what's it called? Fully correlated with the wind speed itself. I'm not actually sure why the wind speed isn't a component, because when I was running these scatter plots, I always included the wind speed every single time, and then when I didn't, then I started to actually get good results. So that's something I need to look more into. It's something I need to do more analysis on, because I'm not 100% sure where it comes from.
Towards the end, when you're kind of classifying the internal waves, you compare the wind speed in there. You don't really talk about it later. I was just wondering if you thought that played a role, or if that was just
plays a role in the imaging. So at higher wind speeds, you get better images. Let me find it. Where is it? Here it is.
Yeah, this one.
There it is. So at these, say, for example, for the RLFs,
so it's Bohr.
So it's probably a Bohr, but not always. I mean, not all RLFs are Bohrs, and not all Bohrs are RLFs, but in general they are. So for example, if you had a depression wave or you had an internal wave and you had really, really poor signal to noise ratio, and because you had low wind, then you might only see like the very front of the first internal wave, and then it comes up as this very faint, bright feature, and I would have classified that as an RLF. I would have classified that as a rough linear feature.
So the wind speeds just affect the radar signature.
Yes, correct.
You wouldn't be able to tell necessarily the depth. No. Because it's just like either or kind of thing you're using it to compare it to, I guess.
Yeah.
So you're just saying the wind speeds affect your radar signature. You get it, not necessarily the type of wave.
Yes.
Okay.
Yes. Exactly. Okay. Well, thank you, everybody.
You're missing a conclusion slide. Like, what have we learned?
I guess I put them all. I threw my conclusions with the category that they went to. So the conclusions of the Doves algorithm are that we found a cool way to get surface currents, and the conclusions of the internal wave type analysis was what the last couple slides where I said which ones correlate with which ones, and then the conclusions of the internal wave Doppler analysis is that the little shifted figure at the end, but for the defense it will have like a overarching conclusion slide.
So the end product is a tool to actually classify these waves, or to...
It's not, it's more of a, I guess it can be considered a tool. It just statistics of what these waves have, what signatures these waves have.
Okay, even more?
Do you have some information about the phase speed of this internal wave? Wavelengths, something?
Say it again, I'm sorry?
The phase speed of this internal wave.
Most of them are going at about 0.2 meters per second. Yeah, in and around there. Okay. Thank
Good.
you, everybody.
Then thank you for the presentation.